here to talk to us about Compute Express Link 2.0. Last year, he was at our workshop and he talked about CXL 1.1. Today, he'll be discussing 2.0. Jim is also not a stranger to our audience here. He's been contributing to OFA and many other industry groups, as his role at Intel is the Director of Technology Initiatives at Intel Corporation. Jim is responsible to establish broad industry ecosystems that comply with new technologies in the areas of enterprise I/O, energy-efficient computing, solid-state storage, and persistent memory. Jim has actually served as a founder and also participated in bringing up multiple industry consortium bodies like PCI SIG, USB, SNIA, IBTA, our very own OFA, and also the Green Grid and CXL. Jim has over 30 years of experience in the computer industry. He's been granted 8 US patents in the areas of computer graphics and microprocessor technology. It is my pleasure to invite Jim and talk to us about CXL 2.0.
Thank you, Divya. Is my audio okay?
Yes, we can hear you well.
Okay. So, as Divya said, Jim Pappas, and I'm speaking today not as an Intel employee, but as the chairman of the CXL consortium. I will say on a personal front, I really love OFA. I've been involved since the very, very beginning. In fact, I called the first meeting of pulling all the companies that were doing InfiniBand together, which formed the group called OpenIB. Jim Ryan, who was working for me at the time, was pulled that together and has been involved since. So I have very deep roots and very high level of respect for everything that Open Fabrics does. It's my pleasure to be here. Next slide. Okay, so the as Debendra did a great opening for my slide, he went through in a lot more detail, but certainly we see the compute infrastructure changing very, very quickly with cloud, with AI and analytics, and bringing that cloudification up to the edge. CXL was designed expressly for this purpose. As Debendra had mentioned this morning, for those of you who saw his keynote, we started with the PCI bus, which is actually, PCI was my first initiative, the original PCI bus, the parallel one. PCI Express was the first initiative I drove that killed my first initiative. So I've been doing this for a long time. Why don't we go to the next slide? So in the CXL consortium, I was here last year. The audience is the same. We were pushing 100 companies. We're about 160 now, just under 160, I think. And so we've almost doubled in the year since I talked to you last. So this is a very, very active consortium. The technical meetings are intense, very, very high level of participation, one of the best I've ever seen in the computer industry. So it's really a lot of fun to be part of this. So, you know, what really determines whether a technology is going to be impactful or not is the ecosystem that develops. And the ecosystem for CXL is, you know, top of class. Okay, next slide, please. So as I was starting to say on 2 slides ago, so we start with the PCI bus and we're increasing its capability quite a bit. We actually sit on the same wires as the PCI bus. We use a technology that lets us switch. In PCI put this capability in called alternate protocol support, and we take advantage of the alternate protocol. So when typically when a system will start up, it's a PCI device that it sees out there. The device identifies itself as having CXL capabilities, and then the protocol switches over to the more efficient and more capable CXL protocol. Fundamentally, what we do is we do this by offering three types of protocols. We call .mem, .cache, and .io. And .io is essentially equivalent to PCI Express Gen 5. It's designed so that it could be dynamically interweaved on a packet-by-packet basis with the other two new protocols that come in. One is called .cache, and the other one's called .mem. And what this allows accelerators to do, and I'll focus on accelerators first, what it allows accelerators to do is have a very tight interaction with the processor that it's attached to. So this really opens up and adds capability to heterogeneous computing, whether it be GPUs, FPGAs, AI accelerators. SmartNICs is one that's going to be, I think, particularly important to this audience. And the last presentation talked about the importance of SmartNICs as an example. And that relationship is so tight that it's essentially the same as two microprocessors that are connected with a coherent interface, where they could, access each other's memory, they could cache each other's memory. The memory attached to either device could be cached locally. And instead of just having this happen amongst identical CPUs, CXL opens this capability so that accelerators attached could also share memory, could cache memory from either side, and could operate out of each other's memory. So what we've done with symmetric multiprocessing, think of extending that beyond homogeneous systems and into heterogeneous accelerator-based computing, so that accelerators could do more. Once again, I think that SmartNICs will be one area that the OFA will be, I think, empowered by. So if we move on to the next slide. So here are it's just showing three different configurations on the top, on all three cases. On the top, you have a processor. In fact, Devendra showed this exact slide this morning. And then in the middle on the CXL, we have different combinations of the three protocols. So if we look at the leftmost, the first, this is on the bottom is an accelerator. That accelerator connects to the processor via CXL, and it uses the CXL.io. Every device has to support CXL.io, but in addition, it's using CXL.cache. That allows the accelerator to cache processor memory, directly access processor memory, and allow the application that's now shared between the processor, and in this case, let's call it a SmartNIC, so that they could much more finely interact together, down to cache level accesses and working with each other's memory spaces. If we move over into the middle, this is very similar to the first one, except that there's memory attached now to the accelerator. So in this case, we're showing it as high bandwidth memory, but it could be any type of memory. And so not only does it do everything that the first example did, but also that memory that's been added could be mapped into and part of the memory address space of the processor that it's attached to. So this would be very similar to having more memory attached to the processor. Either the processor or the accelerator could access that memory, and actually both sets of memory, both the processors and the accelerator's memory, and they could cache it both ways. And that'll be very popular in GPUs, and also probably in SmartNICs as well, especially as SmartNICs get more intelligent and have more processing on the SmartNICs, more general purpose. Excuse me, processing on the SmartNIC. 1 second here. Sorry, there, just needed to clear my throat. Okay, and then finally, the last one is not using the caching or the that at all. This is simply being used as a memory buffer so that we can expand memory. So all of these are use cases that have been here since CXL 1.1, and this is just a a background on where we go from here. Next slide, please.
Jim,
So
I have a question on your previous slide.
Sure.
Can I bring it up? So among
Yes.
the three usages here, do you see a certain way the industry is moving? Is it more towards the accelerator usages, memory usages? Where do you see the industry headed?
That's a great question. CXL was designed with acceleration in mind. If that was the big problem that we were trying to solve. And because heterogeneous computing is here, it's here to stay. And we just needed a better way to do it. And we needed an ability to do it using industry standards. Most microprocessor architectures have a coherent interface bus, and they're insanely difficult to adapt to. I've got some experience, trying to move some accelerators, and it was nearly impossible. Of the dozens of companies who wanted to get going, at best one or two, very anemically made it into the market. It's just too tough. It's just too hard. CXL is an industry standard. It's designed with asymmetric complexity so that the accelerator could be built more simply. So yes, I think the initial reason is for acceleration. If you let me expand on this asymmetric complexity for a second, this comes all the way back to, in my mind, to when we did USB, which became the most, common interface, the most ubiquitous interface in computing ever. And we were very conscious to make the easy to build a peripheral and use the capabilities that were already in the more complex machine it was attaching to. In fact, our model for success was it had to be so simple that it works in a mouse and is affordable in a mouse, which sells for a couple bucks. So and I'm not saying that we're going to build CXL mice. Don't get me wrong here. But that asymmetric complexity was probably the single most important thing that we did for USB and allowed it to reach ubiquity. And if for no other reason, this will allow accelerators to be able to have this next level of being, cache coherent with the CPU at a level of complexity that is not that much more complex than its world today sitting on a PCI bus. I'm not saying there's zero complexity there, but it's low complexity. Now, having said all this, and getting back to the question about memory as well, once you do these three modes that we have, memory kind of comes along for free. Everything that you would need to do a memory buffer is already in place to handle the acceleration that I was talking about. And I would say that we are surprised that memory is coming on at least as strong as acceleration is, and which is good, particularly around the cloud providers. Their biggest dollar spend and TCO spend is in memory, and being able to share and pool memory, or at least have a different attach point to memory, really helps them out quite a bit. So let's move forward now, and I'm going to get a little bit more into the memory here in just a couple of slides. So Devendra showed on the left-hand side of the screen, for those of you who saw his keynote, he showed a similar type of diagram. It wasn't identical. And CXL 1.1 really is down, direct attached to the CPU, and it's a one-to-one correspondence between the accelerator and the CPU it's attached to. CXL 2.0 allows us to move up the stack a little bit. It's not going to be a data center level scale like InfiniBand or Ethernet or others, but it lets you start moving to where you could get to adjacent drawers, or possibly even to half rack or full rack, possibly level of scale, because of a new feature that comes into CXL called switching. So we're moving slightly up in from simple node level to a small collection of nodes. And that is a pretty big advancement, and we'll be going through that in the next few slides. These diagrams on the right hand of the slide were just indicating switches. I got better versions of those in future slides. So let's move forward. Thank you. So this is actually off of what we designed CXL to accomplish. CXL 2.0 is complete, and I'm sure that there's active designs out there right now for CXL 2.0. CXL 1.1 is inside of my company, we have that up and running, and we've done some demos of CXL to date, and they'll be coming in a future processor that our company has. So the rest of my presentation is not on CXL 1.1, but now moving over to CXL 2.0. So I'm going to work and focus on just 3 areas here. I'm not going to go through them all. And so next slide, I'll start with switching. So switching is a very large feature. In fact, I'm going to keep it just to 3 new areas, because somebody smarter than me one time told me that we could remember 3 things, but once it goes past that, it just becomes clutter and we forget them all. So I'm going to talk about 3 things. The first one being switching and pooling. So next slide, please. So here is something. This is with CXL 1.1. We have the host computer, and at the very bottom we have the devices, and there would be no switches in between. So a device would occupy a port. Now what we're showing is that a host could, via a switch, could actually attach to multiple ports at one time. So this is similar to what we see with PCI Express switching. So this is a fan out, an expansion capability. And on the right-hand side, that just shows that we could have, we could gang multiple switches together with multiple ports to have even more fan out. Nothing really too surprising here. It gets interesting on the next slide, so move forward. Here, more complex switching environment. So looking at the left-hand side, here we have the same devices, and now we have multiple hosts. And with multiple hosts, now we can start pooling. So the purpose of this slide is to move beyond just expansion and move it into pooling. So a different host could make requests, and a fabric manager would honor those requests and assign to it resources. And so here you see host 1, which is in that gold color, is attached to device 2 and 3. And so the different devices could request and be granted different numbers of possible accelerators to attach to that. In this example, let's just think of these as accelerators. It could also be memory as well. One thing about CXL switching, we only support right now in CXL 2.0 a single level of switching. Devendra talked a lot about latency, and that's a big reason why, at least in the first generation, we will stick to single level switching. So we won't, you could cascade switches side by side, but you can't go deeper There won't be, you can't create a tree structure of switches in CXL 2.0. Now, if we move over to the right side, so next slide, now I'm showing, these could be any type of multifunction devices on the bottom, but in this case, let's assume that they're memory. So now we have pooled memory. So each memory device could segment its memory into, it could be pages, it could be segments of any size, and that could dynamically be shared between the processors that are attached above. And coming back to the cloud example that I used earlier, right now what the cloud manufacturer needs to do is on each host, they must put enough memory to support their advertised memory per VM. And not all of it gets used, is the problem. So any memory that doesn't get used that's attached to the host becomes stranded memory. It's cost that's in their data center, but it's memory that's not getting used. And that's a large expense. So what this would let them to do is attach a smaller amount of memory direct to their CPU, and then contribute memory to a pool of memory, where at an individual node level, you can still guarantee all of the memory that's advertised, but the heuristics of the system would be such that there could be a tremendous cost saving for the data center operator. Any questions at this point?
Jim, there is a question on the chat that came through. Is there any way you can give us a preview of what's coming in CXL 3.0?
I wish I could, but I cannot. It's, each of these are big steps forward, but the way that CXL is set up, that's proprietary to the working groups. Any company can join the working groups and participate. And CXL 3.0 is under development now. It should be at a 0.9 stage by about the end of the year. And I think that will be another blockbuster.
Okay.
But because of NDA reasons, I cannot disclose it.
Okay. And what is the advantage of using logical devices? In other words, what do you see as applications for this memory pooling with, I guess, single logical as well as multiple logical? Can you talk through applications?
Yeah, well, PCI itself supports logical devices. So you could have, as an example, I'll bring it close to home here. You could have multiple NICs that are attached, in a single CXL device through a single port, and you could have multiple NICs attached, would be an example. In the case of memory, where it really becomes very, very clear, is being able to segment the memory. By the way, probably an important point that I didn't mention, each of these hosts above is living in its own coherent memory space. So those are, up to 16 different processor memory domains up there. Independent processors, independent memory, independent virtual memory, the whole works. So the physical memory is getting mapped in and out. It uses the hot plug and plug and play element. So when a host relinquishes memory, only those blocks of memory will be removed and then reestablished to another host when another host requests memory. So that dynamic allocation happens using the plug and play, but it's using that logical functions mechanism to do it. So it's really, really important in the memory space, because you don't want to have to, you want to be able to share the memory in finer granularity. than you would do with on the right-hand side. If that's a GPU, it's probably just, it will be just associated with one CPU.
Yeah. Okay. And the CXL.cache, it was around from CXL 1.1. What
Yes.
has changed going to CXL 2.0 in CXL.cache mode?
CXL.cache hasn't changed, not in any big way. There's been minor extensions for instance, the hot plug and stuff was not part of the CXL at all in 1.1. So there are, little extensions like that that came in that caused advancements, but functionally it does exactly the same purpose. It allows the device on the bottom to reach into CPU memory, cache it locally, and share that memory with the CPU. So the functions change. What's new in CXL, or we started disclosed so far, is the switching. So that's the first of the three with the switching. So
Okay.
next slide.
Yep. Thank you.
So next I want to talk about, well, here are some of it's actually the question he asked, what are the enhancements to CXL.mem and cache? And some of these I've talked about: function level reset, manage hot plug. But I'm gonna focus on persistence and persistent memory. Those of you who know me know that I've been involved for several years now trying to drive standards for persistent memory through the SNIA organization. We got OFA involved in that in a big way. Paul Grun, I don't know if Paul's on the call or not, but Paul participated with us in SNIA as that interface between OFA and the persistent memory work. So what we've done with CXL 1.1 already supported memory. What we added in CXL 2.0 was all of the functions that are necessary to support persistent memory. And that's a major step forward. So with CXL 2.0, persistent memory really, any company could essentially put any flavor of persistent memory on any CPU architecture, because CXL is being adopted by every CPU architecture. It was very difficult before. It was one of the inhibitors to the growth of persistent memory, was how difficult it is to put into a system. And CXL is doing that with the global persistent flush, the function level reset, and these, and a lot of this goes into the advanced CXL cache and memory support specifically for persistent memory. So if we go to the next slide, this is just a diagram of the, the storage and memory hierarchy. CXL 2.0 is, because of that function, will now allow persistent memory to plug into very easily into a system with industry standard mechanisms to do it. So I'm really proud of this. This is, as a longtime supporter of persistent memory, this is a big deal to me. And I'd also like to thank OFA for their work in supporting remote persistent memory. It was originally called PMOF, persistent memory over fabrics, but it then became RPM, remote persistent memory. Okay, next slide. So that was the second. Now the third area I'm going to talk about is security. So we'll start off by saying that PCI Express is now offering security, and it's called IDE. And the CXL, we're using IDE, the same IDE that PCI is using for CXL.io. If you remember, CXL.io gives you essentially the same capabilities as PCI. And then we've defined similar mechanisms for .cache and .mem. So those are two new areas for.cache.mem. So if you go forward one slide, there we go, thank you. This shows the area of protection. So on the left, you have a root complex. On the right, you have CXL devices. And this IDE, which stands for Integrity and Data Encryption, works across all of the lanes, all of the ports, and including the switches and the device. So now you could have a more secure infrastructure in the system. So that's really it. That does it. This is about the end of my presentation. One more slide, please. And I'm not going to go through the next slide. This I put this in for your reference. Devendra talked a lot about the fact that CXL 2.0 was backwards compatible, just like PCI. PCI is the industry standard for doing this. They've done a spectacular job, and that really protects industry investment, and that really helps ecosystems get created. So this is, you can go through, I mean, you can look at, obviously, if you plug a CXL 2.0 device into a CXL 1.1 port, you're going to get CXL 1.0 speeds. You know, those types of things are obvious. But this, if you go through this thing, this is the whole diagram for all of the connectivity. And we believe that this is going to be really important for the adoption of CXL, because that roadmap of being able to continue to use devices just makes it easy for ecosystems to develop. And my last slide, I think, is a summary. Next slide. Yep. So as we said, we've almost doubled the size of CXL since the last time I was here. I don't know where all these companies come from. we last year when we were here, it felt like we had everyone already. CXL introduces new areas where I talked about switching and persistent memory and security. And in the call to action, you could join the consortium. I'm looking forward to more interaction between CXL and Open Fabrics. I think that what you're doing in management spaces and what you're doing for network management probably could be extended into interconnect management as well. And I think Devendra mentioned it. So with that, I think I took an extra 5 minutes. So
yeah, that's fine, Jim. There is one last question here. You alluded to it, but let me ask again. So PCIe is the underlying core for CXL.io. The .mem and the .cache, I think that's what made you guys form CXL. Was there any reason why you, I guess back in the day, we decided to create yet another separate protocol and did not use PCIe for these usages?
Yeah, well, we use what PCI SIG did is created the opportunity to extend this, and it's open so that anyone can use it. So it was alternate protocol support. So the PCI SIG, looking forward, allowed for protocol to be swapped out and a new protocol swapped in.
Okay.
Why we created a new SIG was opportunistic here in terms of both the PCI SIG has a lot of work to do, and CXL, as you can see, we've done 2 specs in 2 years. So we're on a 1-year spec cadence right now. Mm-hmm. And the next spec is the 3rd spec is due in roughly a year after that. Maybe a year, maybe 5 quarters, possibly. I don't know. It's this is an unsustainable cadence. I'll say this right off the bat. The industry can't absorb technology this fast, but it is such a hot area, and it's such a focus group, and there's so much innovation going into here that we're able to move it forward. Because of the backwards and forwards capability, these will be able to be all interoperate together, and different segments will be able to use different versions all at the same time. But don't expect 1 per year for the duration of time. The PCI SIG, and if we tried to do this in the PCI SIG, which is on a 1-year cadence, I think CXL would have been stalled. So
Right. Okay.
that's the reason we put it in a separate org.
Yep. All right. Thank you. And Duane has a question. Duane, you want to ask yourself? There are 2 CXL devices. You put in a question here. I want to give you an opportunity. Oh, okay. I'll ask. So if there are 2 CXL devices, each attached to a different CXL 2.0 switch, but the CXL 2.0 switch connects to the same root complex, can these devices communicate with each other?
It does not do the direct. They could communicate with each other similarly to the way PCI devices communicate with each other, but not all of the cache, .mem and memory functions are directly. It's more complicated, and I certainly don't have time to go through it now. But I will. I'm not going to say what's in 3.0, but I will let you know that there is industry interest in peer-to-peer communication as well. So that's as far as I'll go.
Okay. All right. Thank you, Jim. So I think I'll use this opportunity to wrap up the discussion here on CXL 2.0. And if there are questions, Duane, please feel free to email me, and we can offline close the loop if there is other clarity you need. With that, I'd like to thank Jim and welcome our next presenter.
Thank you, Divya.